welcome to Osmosiscast. This is episode number 6 of season 2. We're talking about particle physics that makes me feel like a 15-year-old. My name is Callum Morrison. His name is
Jamie McMillan.
Thank you, we got there. So I'm actually gonna derail you right from the get-go, and I'm gonna start with an anecdote. I've been thinking about this anecdote all day. So the story goes, I had a pretty easy time, I think, at school. Nothing was too difficult for me. I did pretty well in my GCSEs, and I consider myself very fortunate for that. I just sort of understood things. Obviously, Jamie and I were at school together, and I remember so many times where there was healthy competition between he and I, and we would always battle to be the best in the class, and it was good fun. And there were times where Jamie was the top, and there was times when I was the top, and we excelled in different subjects in different ways. And I was quite happy plain sailing throughout all of this. And I thought, I worked hard, but I understood it. I worked hard, but I could do it. Until we got to A-level physics. Now, we had 7 in our A-level physics class, and by the end of year 1, it was just me and Jamie. I'm remembering it correctly, and
that was a strong cut. I feel like there was more than 7, but yes, regardless, there was a strong cut of people.
There was a lot of people that did not make it through, and it was fine until one of the A-level physics papers, and I just didn't get it. I didn't get it. And
can you remember which one it was?
It was the one where there was lots of electricity stuff, circuits and power and energy, and so really good that we're now talking about particle physics with lots of energies and things like that, because to be honest, I have felt like a 16, 17-year-old struggling again. So we are talking today, the paper is titled Observation of a New Particle in the Search for the Standard Model Higgs Boson with the ADLAS Detector at the LHC. It's a big famous paper. Obviously most people have heard of Higgs Boson because it's been on the news. These sorts of really big scientific discoveries tend to get talked about in the mainstream, and layman's, which I include myself as after trying to pass this thing, would say, oh yeah, I've heard of Higgs boson. Yeah, I know what that is. Yeah, it gives particles mass. It's easy. It gives stuff mass. Easy peasy, mate. They just found it at the LHC. That's all there is to it. That's not all there is to it. Spoiler alert, that's definitely not all there is to it. So,
definitely not. How confident are you that that is within the public zeitgeist? Because, I was going to say I asked Grandad. You didn't. I'm not sure how many people will say, oh, where were you when, insert X happened? And here, where were you when they announced the Higgs boson?
I don't think it's... No, but I don't think it's not like 9/11. I remember where I was at 9/11. I don't remember where I was with the Higgs boson. Maybe I'm right,
given no context.
Maybe Maybe you're absolutely correct. Maybe I am just absolutely crazy for thinking this is more widely known. Because my perception is that it was in the news, therefore people remember it.
Yes. My perception is I was a physics student at the time, so my perception's entirely biased.
Yeah, whereas I was not a physics student at the time, right? I just saw the news. But no,
either way,
maybe we need some input from our listeners. Have you ever heard of the Higgs boson? I imagine if you're listening to this podcast, you're probably not completely I don't know what the word is, completely in the dark when it comes to particle physics and things like that. I mean, maybe you are. I don't know. Maybe you just enjoy listening to us ramble. I don't know.
I'm sure that can't be it.
But yeah.
Anyway, right. So the paper is talking about the Higgs boson. So this was August 2012. Prior to this, it feels weird that they did an announcement before the paper and peer review stuff. Anyway, so July 2012, they did their announcement, and that was the reveal that they had found the Higgs boson.
Was it really that long ago?
Yeah.
Wow, I'm old.
Yeah, it was a while back.
God, I'm getting old.
It's 12 years back. Unbelievable. So 12 years ago, they announced that they've discovered the Higgs boson, and it was a big deal at the time. I don't know. I felt like it. But yeah, that's what we're talking about. There's a couple of detectors at the Large Hadron Collider. There's CMS, but there's also ATLAS, and this is from the perspective of detection at the ATLAS detector. So, I don't know, Callum, do you want to tell us what you know about I don't know, Higgs. That's lots of I don't knows.
I mean, it is. So the story of me reading this paper is I started and every sentence I'd go on like a deep wiki dive, and I just wouldn't. I'd be like, what the hell? I don't understand. Like I understand why people. I kind of feel like I validated my own job as a teacher, because the stuff that I know and I put onto kids must be really difficult for them. I felt like it was really, really, really challenging to read through. Like even, you know, in the abstract, it talks about. So I got stumped almost instantaneously when it said individual searches in the channels H to ZZ, and I was like, "What the flipping heck's a ZZ?" And then I go down the whole I didn't know this. It's some particles. What type of particles? Don't ask me. So like this. What's interesting is when I came up with the idea of doing a podcast with you, my initial idea was for you to just explain stuff to me, and I feel like this is going to be that. Because I ain't got a clue, mate. You're gonna teach me some things, and I'm very, very excited to learn. To be honest, and this will be a really good exercise for you in science communication, I think.
Yeah, let's do it, man.
Anyway, here's Wilma.
Yes. So I agree. Hi, Wilma. So when I was when you're reading that sentence about the Higgs decay into some Z bosons, like I was reading it like I'm reading words I don't know what these mean, and at least the way that I go through it is I'm like. I just fill in that blank, and I'm like, oh, that's that thing. Oh, that other thing that I don't know, that's the other thing. And I just sort of, like, ignore them, store them in RAM, and then keep trucking along and, like, try and follow the narrative. Like, I don't need to know what that is just yet. So I felt like I got a bit further than that by just ignoring it. I think I went through the whole paper not knowing what the Z was. Like, what is the Z? Is it hadron or boson? I don't know. It doesn't matter. It's just a decay channel, intermediate product.
Maybe I'm reading papers wrongly. Maybe I need to try that in the next one and follow the narrative as opposed to get bogged down with the technicalities.
Equally, like when I go through papers, and I was looking at one earlier this week, and it was just a wall of statistical equations. I was like, I can't do this. So I'm going to read the words, and I'm going to just hop right over these little doobly dogs.
Over the numbers.
Yeah. So, like, I don't know, I got pretty far just by ignoring things and sticking some patterns in RAM. I also came into it with a bit of trepidation, like, this is going to be intense.
It's big.
And, like, the first section or two, I was like, yeah, this is pretty, like, whoa, what are they talking about? Like, gluon fusion to Higgs, or gluon fusion, like, whoa. But, like, I followed it, and I quite enjoyed the narrative. So I'd argue, after reading it, it's a good paper. It's well written. I enjoyed it.
I can't wait for you to break it down for me.
I had fun. Where would you like to start, Callum?
You are in charge. You tell me where to go. You give me a page number, I'll scroll there so it's on the screen for the video watchers. Obviously, the paper will be in the show notes if you are not a video listener and you want to follow along on audio. It is 38 pages. It is a big boy. Is this the biggest one we've done?
I think Desi was bigger.
Was it really?
But it is big.
It's
in terms of actual readable pages. That was a big one.
Okay.
All right, so let's start section 2. You can have a look at a wall of text. So this was talking about the Atlas detector. So context for the Large Hadron Collider. This is a project, I think it's been running since the 60s or 80s. Maybe it's the 80s. So earlier than that, there was the concept of the standard model where I can take it's been like the whole 20th century, but I take an atom and I can break that down into protons and neutrons. I can take that proton and I can break it down into some even more elementary particles. And that's as far as it goes, apparently, but you can split a proton into, I wouldn't even better tell you, I think it's an up, down.
Up,
do you know what it is?
I think it's up, down.
I don't know. We'll say it, you can believe us.
Down, up, right?
Yeah, that feels about right. So you can break down the protons into smaller particles, and those smaller particles there are quarks. I've got did you have my notes?
I can get your notes.
On screen.
I can get them on screen.
Go on then. Pop up the little standard model picture somewhere further down. So the standard model is broken down into, what's that, 12? I can't count right now. 16, 17, including the Higgs, 17 particles. So there are six quarks.
Jamie, why did you posted the picture in here? You should have put a link, and then I could have opened it easier. I'll just type in standard model.
I just got it from Wiki.
I know. I've seen that picture. I'll just get it up quick.
Yeah, there you go. All right. So there's six quarks. There's up, down, top, bottom, strange charm. What do they do?
Which is bizarre, by the way. I always thought these were funny names. Oh my god, I can't find a half decent picture of this.
Well, it's there somewhere. And then you've got leptons, which are... I don't even know how you break them down. There's quarks that have mass and do things, and leptons are just energy things. I don't know. Anyway, you've got some quarks, and then your leptons are electrons, muons, taus, and then there's neutrinos. There's 3 different neutrino flavors. There's 6 leptons there. And then they're your standard model of things, stuff in the universe.
So basically, everything that has ever existed and will ever exist is made of these ingredients.
Yes, they are your core ingredients to make your cake.
Yeah.
The mechanisms. I like cake. The mechanism by which your cake sticks together and interacts is managed by your interaction bosons or your force carriers, whatever.
This is the part where I am lost.
I don't know where I was taught standard model stuff, because I don't think it would have been in uni. So I think it must have been in Scott's class.
Ah, yes.
Or it could have been the old WIMS.
I think it was Mrs.
I can't remember who taught us.
I think it was Mrs.
Either way,
Scott.
okay, so Scott. So I think my only taught knowledge of standard model shenanigans is
me too.
Is from A level. So
I loved it, by the way. I loved the standard model.
It was great.
It was so good. So good.
Great time. I was always really keen to go and work at the LHC. Maybe it's just because it seems so wild.
Maybe you should.
No, I don't know. Not right now. No, maybe.
Too many little ones walking around. Maybe in 20 years.
Yeah. It's a cool place, though.
It's humongous. I have got the picture you shared, the diagram of the LHC, so we can reference that later as well.
Oh, yeah, I'll come back to them. So, how many forces are there? Elementary forces. So we've got gravity.
The strong force.
Electromagnetic.
And the weak force.
Strong and weak nuclear forces. So that's it.
Those are the only ones I know of. If there are any more, I don't know about them.
I think that's it. So they're your 4 forces. So working backwards. So the strong and weak nuclear forces, they're managed by the gluon, the Z boson, and the W boson. So that's 3 of your bosons. So they do, I don't know, they do fields, and that gives forces. Wild stuff. Your photon is your electromagnetic, so that's how we see things. And within the standard model, there was a description of gravity. They knew it's a thing, but there was nothing that gave things mass, so gravity couldn't exist. So there was in the description of the standard model, there was a hole. And from describing that hole, it's like having a puzzle with a piece missing.
You know the shape of the puzzle, yeah.
Yeah.
That's a great way of putting it, by the way. I really like that.
Yeah, I thought so.
That's really nice.
So you've got your puzzle, you've got a missing piece. You're just trying to find this piece in, I don't know, your big puzzle box. So basically, Large Hadron Collider finds puzzle pieces for you. And so from the description of the standard model that they had and the properties of this hole, they could narrow down to, some ranges of, it should be this mass, it should interact like this, it should come from... Here's a description of a thing. Find something that matches.
I was just thinking. So I always think back. This has just made me think of Mendeleev's periodic table and how he left gaps, and he predicted what would go in those gaps in the future, which is a GCSE thing, which I teach the kids. It's a really, really nice parallel there. Actually, I like that.
Yeah, that's good. Nice.
That's good.
So, that's kind of all it is. It's similar to the periodic table, just at a smaller scale. So that's why they were looking for Higgs, because they wanted to complete their standard model and describe how things worked. Anything else on that? There's a bunch of other words that get flopped around, like hadrons.
Can you tell me what a hadron is? I don't even really.
I think a hadron is just a collection of quarks. So, a proton's a hadron.
Okay. because this was a wiki page I was on. There was I'll see if I can find the graph and share it with you. Yeah, this is the graph. I might actually this is going to be really scuffed because we're recording podcasts, but I'm actually just going to share it to you, and I'm just going to screen share you.
Are you kidding me?
I'm actually just screen sharing you.
This is wild.
You can see it.
Right.
This is the graph
Hadrons.
that I was I was just looking at, and it took me so long
to pass
through it. Well, it does, because you're right. Hadrons, protons, and neutrons are baryons.
Okay.
So they're under that umbrella.
Okay. Right.
And then electrons are not hadrons.
I don't understand.
This is. Do you know what's really interesting to me? You seem to have passed this paper relatively well, and you haven't seen this graph.
No.
This diagram. I honestly, trying to pass this diagram next to ZZ bosons, which are under bosons here, this killed me. And you haven't even seen it. You haven't even seen it. That's so wild to me. Like, maybe I just came at this completely the wrong way.
I don't know. Maybe that's
I mean,
I guess I read papers by skipping a lot. This one I read a bunch.
I just think it's really
default approach.
I think it's really impressive that
it's fun.
These different. I think I could, as a from a growth perspective, I think I will take that and maybe not be so literal in the future, because I really did get bogged down trying to understand and define these words: boson, hadron, fermion, baryon, meson.
It doesn't matter. It's just a particle, man.
It's just okay. The physicist said it, not me.
Okay, so if you've described your hypothesis, find me a thing that fits in this puzzle. The next thing is to design your detector that does this. So at CERN, Centre of European Research for Nuclear. I think it's like a nuclear research thing in principle. And they've been running for many years at smaller. Did I send you the picture of it going from level to level to level? A Large Hadron Collider?
Possibly.
I feel like I said.
Is it in your show notes? I can bring it up.
Large Hadron. Upgraded over time. There you go.
I have got it.
You can see a bunch of circles.
Is this the facts and figures about the LHC? What is the LHC? Why is it called the Large Hadron Collider? How does the LHC work? Yeah. Yes.
Picture with a bunch of lines.
This is the one that you said, this is a good diagram. This is what I mentioned.
This is a great diagram.
Yes, cool.
Whenever I think about the Large Hadron Collider, this is what I think about. It's not just, hey, look, we built this thing and it does a thing. This has been an ongoing research effort for
many years.
Decades at this point. So when you think about what the Large Hadron Collider does, it takes some hydrogen gas, which is basically protons, and then it accelerates them really fast and smushes them together and looks at the pretty fireworks. But what you can see from this diagram is actually to get up to the speed required for the Large Hadron Collider, there's a bunch of earlier,
smaller ones,
smaller, loops or accelerators. So accelerators, you can get linear ones, get circular ones. I'm trying to see if you can see an injection point on it. I don't know if you can. Anyway, so at some lower level, there'll be hadrons or protons thrown into the mix, and they'll start accelerating up, and then they'll be siphoned off, and they'll run up to the next one, so they'll run around SPS, and then they'll get siphoned off and run up to the Large Hadron Collider. So that's I always find that.
Sheesh. It's big, isn't it?
It's big. Look at it on a map. It's a big thing.
Yes.
So you've got this big circle, the particles are whizzing around really fast, and they collide at a couple of detector sites. So there's CMS, there's Atlas, and there's Alice. Anyway, so that's ongoing effort. Build up a accelerator over time and years of research. And the Atlas detector itself, I don't know, maybe we can say a couple of words over the detectors, but I think I had as a poster in my childhood, in my formative years, the poster sitting on hung on my ceiling as I went to sleep was the Large Hadron, was either CMS or Atlas.
That's cool.
And just seeing this, and you could see like a tiny person perspective. But
I might find a picture while you wax.
Yeah, I think the other link I sent on Atlas, right at the top, Atlas. Probably a good one. Yeah, look at that. So it's just like so you've got a big circle where things are whizzing round, and then around the circumference of at one of these points, you've got lots of detector elements, and that's your Atlas detector. And the things that are in there are calorimeters, so measuring energy of things. There are silicon pixel detectors, so they measure, charged particles, so they can measure electrical charge. There's some microstrip detectors. What do they do? Reconstruct tracks. So a lot of the different types of detectors within Atlas, they're trying to, if there's a big explosion, fireworks coming out from everywhere, you want to be able to trace the direction and velocity of those firework particles, and then run them back to your collision point. So if you can do that, then, because it's not necessarily collision and then they all explode to their final forms. There's often evolution and decay, so it might collide and then create some. So what we're seeing on page, the HWW stuff. Let's.
If you give me a page, I can get to it easier.
Just go back up to the abstract. Abstract, I'll have it. So where you see Higgs decays to ZZ, what that's saying is, well, actually, no, maybe we don't want that. We want the production methods. Production methods. That's it, section 3? I think, yeah. Higgs Boson production processes. So section 3. So rather than it just all exploding to Higgs or whatever, it will explode to, so like the first example here is a gluon-gluon fusion. So you might have two gluon particles that
you're going to have to give me a page,
process of explosion. I'm looking at just under section 3.
Why? Hang on. I'm clicking. Signal and background simulation samples.
That's the one, yeah. You can't see much other than
just words.
Yeah, it's just words.
Just many words.
But if you take your gluon and gluon and then they crash into each other, then you've got a separate explosion. So you're trying to not just follow a single explosion back to its core. It's like tracing explosions from other collisions and decays. So you might have it was the other. So one of the detection channels for the Higgs is a Higgs boson just decays. It's not stable. It just decays to two Z bosons. And then those two Z bosons then decay further to 4 leptons. And you're just it's tracing all of those lines from the various production mechanisms to their point of origin.
It's absolutely freaking wild, to be honest.
Wild. It's crazy.
It's definitely a more complex magic system than in Harry Potter.
Yeah, big magic system.
Ever since we said this in the podcast a few episodes ago, it's all I can think of whenever I think about how cool science is. It's just no, magic is actually real. It's just really hard to do.
Yes.
That's wild.
So, yeah, you've got a bunch of things exploding, and, well, I did some scribbles about the production mechanism, but that's boring. So the way that they approach,
it teaches me something.
Nah, we'll get there if we get there.
Okay.
So in detecting the Higgs, they're trying to find what are the decay channels that spawn a Higgs or originate from a Higgs. So what we can have a look at, probably section 4, I'm assuming this is. So this is Higgs decays to 2 Z bosons and then further decays into 4 leptons. Channel. So what that means is there are various channels. I don't know what this really means, but as I was reading it, they can pull out, if you have this explosion of material, you can separate a bunch of different events into different groups, channels. And so I can say this group of events is detected by this series of detectors. And so for this one particular channel, the predominant thing they're doing is taking all of these events within this channel, so all of the particular leptons that are floating around and exploding out from other events, and then they're tracking them back. And they're saying, can I take these 4 leptons and can I trace them back to a single origin point? At which point they would have been 2 Z bosons, and then I can think further at how they propagate. So at least the way that I was reading the work that they're doing is they've just got immense amounts of data that are telling them about direction, velocity, properties of a particle, like is it a positive charge, negative charge, so you can give it a label, like that's a lepton, electron. And you can find out where it's come from. And then just finding the needle in the haystack. So they're just throwing away some of that chaff and saying, well, these events, they don't make sense. They don't fit the criteria for this particular decay route. If I took out these 4 arbitrary leptons, if they... I just got balloons on my screen.
That was really good timing.
Visual only. If I take these arbitrary 4 leptons and they don't match my criteria that I'm ascribing, therefore they can't come from a Higgs.
Yeah.
Throw them away. Take another 4 leptons. Oh, these could come from this production channel or this decay channel. Decay process. Because they have the right spins and the right charges and the right velocity. So that's predominantly what Section 4 is saying. We applied a bunch of these criteria and we think all of these events come from a Higgs.
So I actually have a joke for you.
I love jokes.
A Higgs boson walks into a Catholic church. The priest says, "You can't be here." And the Higgs says, "You can't have mass without me." That's my response. This is wild. It's just completely wild. You know what though? I really appreciate your explanation and your patience.
Thank you.
To pass this because I don't know. I feel like I don't have the brain waves to appreciate just how much work has gone into it. I just don't. But that's why I hit you with the Higgs boson joke.
It's a good joke.
That's all I got. That's all I got. So
that's fair enough.
Obviously, this paper outlines 3 main channels.
Is 3?
I think so.
Yeah,
Chapter
3.
4, 5, and 6.
Mm-hmm.
Are there other ways?
Other than those 3?
Surely there must be. I don't know. I haven't done any further reading.
I don't know.
Fair enough. Maybe there are. Maybe there aren't.
These are the only 3 I know in terms of detection channels. So TLDR is you have 1 million lines that you're trying to follow. Some of them don't make any sense.
One of them matters.
One of them matters. Find the one that matters. Plot it on a graph.
And find your Higgs.
So we can hop down to trying to figure the first one I can see, figure 1. So this
still in section 4.
I think so. Yeah, it's a big.
Got a page
section.
number?
No, 6.
The graph. I looked at this graph as well when I was doing my reading, and this is where I was confused. So I was like, "What's ZZ?" And this is as far as I got.
Yep, that's fair enough. So actually, let's go to figure 2. It's a bit better.
Okay.
Figure 1 is talking about the subleading lepton pair, and there's not much signal there for the Higgs, but figure 2 shows it a bit clearer.
I'm zooming on figure 2. Talk to me. Help me understand this wild looking
if I'm
graph.
saying there's a bunch of these events, what these are describing is there's a bunch of signal from, so in red I can see signal from these ZZ bosons, and I'm detecting them, and they have this distribution of mass per.
So is that mass on the x-axis?
This is like a histogram, basically. A histogram shows for each of the things on the x-axis how many of them are there.
Okay.
So what you can see if you look at this, there's a big hump at 200 gigaelectron volts. So that just means there's a lot of events.
Yeah.
The most events are at 200 giga electron volts.
Giga.
Giga. And that's saying this. We've ascribed all of these events to this background signal. All of these events I can describe as ZZ measurements or detections. There might be some background from Z jets and top quarks, the purple line. But there is this little blue section here which says these are our Higgs events. These are the events that we think describe a Higgs. They're in this mass range, and the important thing is that peaks up above the background.
Yeah.
So if it was just a tiny little hump like you see in Figure 1, that's saying, well, I don't really have much
You
clear...
might ignore it. Could just be noise.
It could just be noise. It's within my uncertainties.
So are the black bars uncertainty bars then? The dots
they are.
And the
they're
bars,
the... Does it say what they are? Doesn't. But yes, I think they're the uncertainties for each of those measurements. That's their actual data. Okay, I think the black dots are their data, and then the coloured bits are the... I think they're fitted against the standard model.
Okay.
That's like expectation value.
Imagine being in the room.
So if you took away those colour bits...
Yeah, I was just saying...
If you took away those colour bits, that data would look like even less.
Yeah.
So that's some good data presentation right there.
Mm-hmm.
So that's kind of what they're doing. I've got a bunch of events, and I can ascribe them to these different things. And here's some Higgs things. I think these are Higgs things. And then the next important thing to do is, if I have these Higgs things, can I be so confident that these can't be random gubbins? So then there's a whole nother swathe of stuff about systematic uncertainties and how they account for those and correlations, which nice. It's nice. I like that.
I just like that you managed to help me understand this graph.
You follow the graph?
I follow the graph.
Hey, nice.
That's a win.
Blue bit sticks out. That's good. That's a win. That's a win. So if we hop over to... So section 5 is talking about the Higgs decaying into 2 photon channels. So this is like more of the same. I've got a bunch more events. I've detected all of these photons. And I'm going to throw away a bunch of chaff because these can't come from this production channel.
Right.
Or this production process. These would not come from a Higgs. So you throw away the rubbish, you keep what you do have, and you throw it on a mass distribution plot. And I guess I'm having a look at, it's probably Figure 4.
Figure 4.
And, I don't know, you have a look at it, there's a line, and then there's a little peak at the 126 gigaelectron volts, which is kind of what they want.
Is that the same position that the peak was in the last graph?
Yes. Yeah. 126 gigaelectron.
God, imagine being in the room where you look at this graph for the first time. That must be a feeling. I'm understanding it for the first time 12 years after it was published, and I'm thinking, whoa.
We got this little kink. Oh, this might be it.
Yeah.
Yes, so it gets better. I don't know. Can I say that?
It's like a movie. Hello, Wilma.
Final channel, they had a Higgs decaying into 2 W bosons, and then they decay into an electron and a muon and 2 neutrinos, so another 4 leptons. So yeah, there's another decay process. So they had these 3 channels, and they were presented in order of like signal for Higgs. So the first one, the Higgs to Z bosons, is like the best signal and the clearest signal from their measurements. Mm-hmm. And that's accounted for in their uncertainties when they start globbing all these 3 channels together. So what was... Let's skip forward a bit to... where's the figure with the dippy line? There's a dippy line. It's probably in section 7 or 8. Yeah, I like that one. Yeah, let's go for that one. 7 and 8. Figure 7 and 8 on page 18.
Can you hear me?
So this... Yeah,
I just had to unplug my microphone and put the dog to bed. He was being a pain.
That's unbelievable.
Where did you say figure 7?
Yeah, figure 7, page 18. So these are... I've now thrown it all together.
Do you mean table 7?
No, figure 7.
On page 18? Oh, wait, I'm on page 17.
Okay, next page.
I'm with you.
Yeah. And so here what we see is a big dip at the 126 gigaelectron volts. So that's really good. But I guess I'll draw your attention to, so if we have a look at figure 7b, the little like middly plot here.
Mm-hmm.
So we can see signal expected is the dashed line, and it sort of drops off into saying we expect no signal in these regions. And that's based on their current constraints of Higgs-like things. So it wasn't actually like we expect the mass to be between like 120 and 130. It's 126, it's bang in the middle, that's great. There's actually a wider range of values it could be. So like if you look at this, it could be up to like, I don't know, about 140 or so gigaelectron volts. They say it can't be like 150 to 200 gigaelectron volts mass, but actually it could be all of these heavy masses. So it wasn't such a narrow window of constraints. There was some bigger.
It's very, very broad.
Yes. But if we have a look at the solid line, what we see is that dip there. It says that I think I described that, but that's fine.
Trust you.
But what we see from this dip is we expect the observed signal at that point should be super confident. So we can see it dipping all the way down to 6 sigma, which is a statistical probability thing, which says we're really confident that the signal at this point is going to be really low. And I think that's what that's saying. The local E0 stability as a function of mass and expectation. Yeah, okay. So that's saying basically we're really confident that the signal that we're seeing at this mass is not noise. So an important aspect.
And I imagine in this paper they go into a lot of detail about how they can be so confident in that. I don't think we're going to go into that now because I imagine.
We're not.
That sort of statistical stuff is, I imagine, quite dry.
I'm not on board with it. I'm on board with it, but not right now. So they're really confident, and there's a peak at this mass, and they're very certain that it is a signal and not random noise. Was like the
epic
shining goodness of epicness. So that right there, figure 7 and 8, they're your results. There's a dip. So they're really confident about it.
Would you say that figure 7 and 8 is the meat and potatoes, Jamie?
That is the meat and potatoes.
The special sauce.
Dang, Nabby, you're right. Yes.
I love that.
That's it. That's the highlight of the paper. Yeah. What else did I chat about in my notes? That's about it, really.
There's some stuff
about some stuff, and figure 7 and 8 are the meat and potatoes. So that's kind of it. If you're interested, read the paper, have a look at figure 7 and 8. Very exciting. I really enjoyed the paper and found it easy to read. That's again because I ignored a bunch of stuff.
I got 2 paragraphs in and gave up. I unironically got 2 paragraphs in and gave up. Oh my lord.
Yeah, there's a bunch of other stuff. Yeah, there's some other statistical stuff saying like we think it's here and some bounds of our constraints. But that's Higgs. They detected it. Pretty cool.
It's pretty cool. I mean, I'm actually shocked that this was 2012 because this feels like it was like 2018. Like in my like,
it doesn't
how
feel that
old
long ago.
have I got? That's crazy.
Yeah, it was a while back. So since then, so that was 2012, and so cool stuff that was happening at the Large Hadron Collider at that point. So I can't remember if I took scribbles of. I don't think I did. But when they were building the Large Hadron Collider, it was a couple of years to get the speed up and up and up. And the reason, and if you follow any of the narrative of Large Hadron Collider stuff or certain things, it's all about more power. Can we get more power? And the reason here is if we look at the figure, it was like figure 1 or something where you've got the little like peeking out. If you're not at those higher energy levels, that little peak of Higgs signal is just too small and it's not peeking out of the background noise. So that's the large reason for more power. What other shenanigans are they up to? Either way, so that was at 8. So this measurement was released at 8 tera electron volts collision energy.
It's a bit big.
Big. So there's a lot of energy going into that collision. since then, I think they're now up to 13.6 tera electron volts. Anyway, so in the last 10, 12 years, they've got more power out, and I think, well, maybe it was 2018.
I mean,
they did another.
Are there more particles to find?
Hop onto the Atlas and CERN website. It was a super cool resource. What other shenanigans are they up to? They're trying to figure out dark energy things. They want to make more Higgs bosons so they can then understand the properties of it further. What others? I can't remember what they're up to.
Lots of interesting
but there is
things. Very confusing and very high-tech things.
Very high-tech. Have you been to CERN? I assume not.
No, have you?
So I feel like I would know about that. No, I have not.
Maybe we should take a holiday.
And they have also been there. It would be really cool.
Let's go to CERN. We could go to CERN and we could do a vlog. God. No, but
where was I going with that?
I don't know. Where were you going with that?
Timescales. So the timescales of saying they were designing the Large Hadron Collider, which was this upgrade to their existing colliders in '95.
Really?
And it took 15 years to design, develop, build, operate. 2020, they submitted their technical design review report for the next generation of collider, which is the high luminosity Large Hadron Collider. As I understand it, it's just upgrade some of the components so they can go more energy.
It's all about more energy.
Yeah, give me more energy. And I got a couple of other ones coming up, but yeah, that was
stuff.
That's pretty cool. But it always impresses me when I think about the timescales and the collaboration, the sheer amount of effort to
build it and
put it all
do
together.
It. Yeah,
just to do it.
It is. I mean, it is. I think like an achievement of mankind that we have learned what we have learned.
It is. Yes, agreed wholeheartedly. It's a cool thing.
And you know, they've learned all that just so I can come on here and go, it was quite hard to read.
They could have done some better comms.
I had trouble passing all that data. Oh gosh.
Yeah.
All right. I mean,
more trivia.
Please carry on. Trivia me up.
Maybe this is my final thoughts. So, Callum.
Yes.
How much? So, if we're doing proton-proton collisions, hydrogen is basically a proton.
Yep.
It's a stable form of a proton. How much in the years of operation? I think actually it's about to like 20. In its years of operation, how much hydrogen do you think the Large Hadron Collider has used?
How long is a piece of string? I mean, I imagine it's a lot.
Okay, I will give it to you. Would you like to give the response in moles, because you're a chemist, or would you like to give the response in like gas cylinders, so 230 bar gas cylinders that you'd see on the back of a gas truck?
It's got to be in the region of like tens of thousands of gas cylinders, surely.
I think I would probably think the same.
Yeah. Go on, how much?
Less than one. They never replaced it. They use so little fuel.
Is that because they're using like singular particles in their
but yes,
collisions?
It's more than singular, but like it is like it's like small amounts.
Right.
When you compare the amount of moles, like I know, less than a cylinder. Thank you, Molly.
That's the best thing.
So in one mole, I know, right?
They've spent like no money on that.
Hang on, well, that's not quite true. Yeah, if we think about the operational cost, that is expensive. But if you take like one cylinder of gas, that's like 230 bar of that pressure. So the volume in there would be like a lot. And 1 mole is 6 to the 23 particles. So really, like, in one cylinder, there is a lot of
many particles.
Like, many orders of magnitude.
Mm-hmm.
But the amount they need is, like, less than Less than a cylinder.
Less than a cylinder.
Which,
in the year? Is that in the whole time? It's been.
I don't know if it's the whole time. I can validate it later, but it's in like multiple years of operation, which is
Let's
still
just
enough.
say
Like
it's
that's
the
still
whole
really
time.
good.
At that point, it's
Let's
the
say
whole
it's the
time,
whole
isn't
time.
it? That's crazy. I genuinely.
Which when I think about.
Yeah.
I think about being in my lab and we'd use like a cylinder of nitrogen and we'd be using that to purge an atmosphere. Yeah. You turn it on and it's going through some reasonable couple of litres per minute. Pissing gas out into the wind. Mm-hmm. This Large Hadron Collider.
Efficient. Yeah. Oh, I love that. I mean, so I guess my final thoughts. I have two. One is sort of about my approach. I feel like I got less out of this paper because I got so bogged in details that I didn't get. So I'm going to take that forward with me. Nice. And secondly, I think I've already said it. Just that this is like just the fact that human beings are at a point where like we can pop on the internet and learn about this sort of stuff. I just think it's absolutely crazy to me. I feel like I say that every week. Like this is absolutely crazy to me. At what point is it going to stop being crazy? It is. But this is what I say. Like when I get kids at school that are like, "Oh, this is so boring. Why do I need to learn about this?" I'm like, "Well, I find some things in science boring. It's okay, but like there is something for everyone, you know." Mm-hmm. And it answers the big questions, or it attempts to answer the big questions.
And this is such a subset in the whole
this is
whole grand scheme of science. Yeah? This is just particle physics.
This is
thinking about biology, pharma.
This is like 0.5% of physics. I mean, maybe,
and it's still so epic.
But it's still huge, and it's so good, so cool.
Yes.
I think that's probably a good spot to wrap. Then, what do you think?
I think so.
Okay. Well, where can people find us, Jamie?
You can find us on just head straight to our website, osmosiscast.com. You can find links to various places. We're on YouTube, we're on Spotify. We're trying to be other places, but we're not right now.
No. I chronically hate social media, so it's really hard to do it. But hey, we're having super loads of fun doing the actual podcasting bit, and that's the main thing.
Do we have a Discord server?
Not yet, but we will.
Working on it.
So our intention is to have a Discord server, and we will update you with that information as it comes out. Hopefully by the end, maybe by the end of season. If not the end of season, then certainly between seasons, I think we'll have it ready.
Sounds good. So next time you'll hear us will be the end of season 2.
That's exciting.
Very excited. I'm really excited for the next paper, by the way.
I haven't read it yet.
It's a banger. It's so good.
No spoilers for the listeners. No spoilers, but it's going to be a good one.
All right.
Right.
Yep. Looking forward to it.
On that
I'll see you then, Callum.
Thank you very much, everyone. See you later. Thank you, Jamie, for taking the time to teach me a thing or two. I appreciate it.
Take it easy, man.
Ciao.
Bye.